Hello and welcome to another Reigate Maths Further Mechanics video. So we're carrying on with the work on oblique impact, and we're looking at a couple of different examples and also the impulse that the particle is subjected to. So the impulse on the particle will be perpendicular to the surface, and the impulse is the change in momentum perpendicular to the surface. And you need to remember to take account of the direction of the velocity. So we've got impulse is final velocity, take away initial velocity, and there'll be a sign change there to work on. It's important to realise that oblique impact can also result from vertical motion. So two different examples of that sketched out here. If you drop a ball onto an inclined plane, then it is essentially approaching that plane at an angle, and it will bounce off at a different angle. This particular example shows it coming off horizontally. It won't always. It might come off at an angle down like this. The other way that oblique impact can happen is if you bounce something and it's bouncing along, possibly like this, bouncing and bouncing. As it approaches here, it's got a velocity at an angle to this surface. So this would be an example of oblique impact of something bouncing along the ground. So let's have a look at these questions. So the first one has a ball of mass 2 kilograms falling with a velocity of 20 meters per second, striking a smooth fixed plane which is inclined at an angle of 60 degrees to the horizontal. So you need to draw a nice clear diagram for this. So we've got an inclined plane like that, possibly using a ruler even, and this angle on the plane is 60 degrees. Now the ball is falling vertically, so it's coming down vertically like that with a velocity of 20. The coefficient between the plane and the ball is 0.4. And it's going to bounce off at an angle like that. Try not to draw the angle as being horizontal, because otherwise you might think that it is and you're working. So it comes off with a velocity of v, and that angle there is beta. Now we need to work around and work out the other angles in this diagram. So if I draw in another horizontal here, I know this angle is 60. This is the vertical, so that's 30 degrees there that it's coming down at. Right, so we're asked to show that the angle the final velocity makes is 13 degrees. So we're going to do exactly the same as we did before. We're going to resolve horizontal to the plane, or parallel to the plane rather. So parallel to the plane. So we're resolving in this direction. So the velocities will be unchanged. So I've got 20 cos 30 equals v cos beta, and that's going to be equation 1. Perpendicular to the plane, I've got 20 sine 30 multiplied by e, which is 0.4, is going to be v sine beta resolved in that direction. And I'm going to call that equation 2. So I'm trying to find the angle, so I'm going to divide equation 2 by equation 1. So equation 2 divided by equation 1. So equation 2, that's going to give me tan of beta. I divide this by this, is going to be equal to 20 sine 30 multiplied by 0.4 divided by 20 cos 30. Just always double check that you've got everything in the right place. So we've got sine over cos, and then this equation here over that one there. This is going to simplify to give me 0.4 tan of 30. I'm trying to find what beta is, so I get from this that tan of beta is 0.4 over root 3. And that gives me that beta is equal to 13.0 degrees. Part B asks you to look at the impulse on the ball and show that it's 28 Newton seconds. So impulse is change in momentum. So we need to say that's going to be the mass of the ball too. Then we need its velocity at its final velocity, which is v sine beta, minus its initial velocity. And its initial velocity is minus 20 sine of 30. So just watch here the signs of your equation. The final velocity is in this direction, v sine beta. The initial velocity is in the opposite direction, so it has the opposite sign. So working this through, we can say that's equal to 2 multiplied by, we can look back to equation 2 here. We've got v sine beta is equal to this expression. So I've got 20 sine 30 times 0.4. Multiplied by sine of beta. So v sine beta is 20 sine of 30 times 0.4. An extra sine beta in there, so we just need that bit there. And we're going to add on 20 sine 30. And when you work that out, you get 28 Newton seconds. Sine 30 is a half. Sine 30 is a half there. That all works out. So we've shown that the impulse on the collision, on the ball during the collision is 28 Newton seconds. Looking at the second example in this section, we've got a smooth sphere, mass 200 grams, so we're going to call that 0.2, moving on a horizontal plane with a velocity of 4 minus 5. Now, it's worth just sketching this out so you've got a picture in your mind of what's going on. The initial velocity is 4 minus 5, so it's approaching the wall like this. It's going to collide with a smooth wall, which is parallel to J. So here is the J direction, and this is the wall. And it's coming in like this. And we already know the two components. It's coming with 4 and then 5 coming downwards. We know that E is equal to 1/4. And we want to find out what happens afterwards. So it's going to bounce off afterwards like that. So let's look parallel to the wall. The velocities will be unchanged. Now, parallel to the wall, its velocity here is minus 5i. So before, it's minus 5j, because it's coming down. So after, it will be unchanged. It will still be minus 5j. Perpendicular to the wall, it's coming to hit the wall with a velocity of 4. So we've got 4 is the incoming velocity. Multiply that by E. That gives me the velocity that it comes away with. So that's going to be 1. But of course, it's in this direction. So the velocity afterwards, after impact, is going to be minus I minus 5j. So you could set up an equation calling this xi plus yj, but you do need to be careful with the signs of your components, particularly the rebound here. So we've got the velocity afterwards. We want to find the KE lost. So for part B, the kinetic energy lost is going to be a half mv squared, the initial KE minus a half mv squared for the final. so possibly we should call that u. So that's going to be a half multiplied by 0.2. I'm going to take that out as a factor, and the velocity before, the speed before, is 4 squared plus 5 squared. So that's v squared minus 1 squared plus 5 squared. And let's just check we've got enough brackets. There we are. So that's a half m on the initial speed, take away the final speed, but both of those being squared because we're finding the kinetic energy. And that is equal to 1.5 joules. Now, part C asks for the angle of deflection of the sphere. So we need to use the scalar product for this. What we've got is the incoming velocity is 4I minus 5j, and then the outgoing velocity is minus I minus 5j. And we want to find the angle between those two vectors. So in order to do that, we're going to use a scalar product. So I'm going to say 4 minus 5, dot product of that with minus 1 minus 5 is equal to the modulus of the first vector, 5 squared plus 16 squared. 5 squared plus 16, it's going to give me root 41. Here, this is going to give me root 26 cos of theta, where theta is the angle between the two vectors. So working that through, that gives me cos theta is equal to, this is 25, take away 4 is 21. And I'll work out the scalar product there, divided by root 41, root 26. And that gives me theta is 49.9697, which we can round to 50 degrees. And notice that that angle of deflection, if I carry this vector on up here, that was the incoming velocity. So that is the angle there through which the velocity has been turned as a result of the collision. So this is an example using vectors. It's the same principle as before, just need to watch the signs when we're dealing with the components.